In 2022, a team of astronomers working with the Murchison Wide Field Array detected an unusual radio transmission that appeared every 22 minutes. At first, this didn't seem too out of the ordinary. Repeating signals are often traced back to pulsars, which are rapidly spinning neutron stars, emitting powerful beams of energy as they rotate. But when researchers dug through decades of archived data, they discovered something astonishing. The same signal had been reaching Earth consistently since at least 1988, showing an incredible level of stability that no known pulsar should maintain at such a slow rotation rate. If this source was a neutron star, it was unlike any ever recorded. So what exactly was producing this strange cosmic rhythm? I'm Mike, and you're watching Universe Unfold. Today, we'll dive into the enigma behind this signal, one that may rewrite what we know about the most mysterious and powerful objects in our universe. The celestial object, designated as GPMJ 1839-10, lies approximately 18,000 light-years from Earth. The signals it emits arrive as pulses that can last anywhere from 30 seconds to as long as 5 minutes. These pulses don't follow a perfectly predictable schedule. They tend to occur within a window slightly over 6.5 minutes wide, centered roughly 22 minutes after the last one. To the casual observer, that might seem like an unusually inconsistent pattern. A difference of several minutes in arrival time and such wide variation in pulse duration doesn't sound like the mark of a steady cosmic source. However, things are rarely that simple when it comes to neutron stars. Their inner workings are chaotic and extreme, influenced by gravity, magnetism, and quantum effects that are still not fully understood. So, if this source truly is a neutron star, there could be several physical factors responsible for these fluctuations in pulse length and timing. Despite this apparent irregularity, astronomers managed to extract this faint signal from 35 years' worth of radio telescope data. By expanding their dataset and averaging out the inconsistencies, they determined that the source rotates once every 21 minutes and 58. They also measured how its spin may have slowed during that period. Yet, to their astonishment, they discovered that the rotation rate has remained effectively constant for over 3.5 decades. Now, that's not what scientists expected. Normally, as neutron stars emit energy into space, they gradually lose momentum and slow their spin. But in this case, the data shows that if any slowdown occurred at all, it couldn't have increased the rotation period by more than 0.2. That's an unbelievably tiny change, essentially imperceptible, suggesting that whatever this object is, it's maintaining an almost perfect rotational stability. This kind of stability isn't strange for most pulsars. These cosmic lighthouses are some of the universe's most reliable clocks. Their regular pulses are so dependable that astronomers use them to keep time over astronomical distances. But here's the catch. Such precision is incredibly unusual for a pulsar spinning this slowly. To understand why, we need to revisit what pulsars are and how they gradually lose energy. Pulsars are the ultra-dense remnants of once massive stars. Neutron stars left behind after a supergiant collapses and explodes. Aside from black holes, they are the densest forms of matter in existence. To appreciate that density, consider this. Ordinary matter, like the stuff making up Earth, is mostly empty space. Atoms consist of a tiny nucleus, surrounded by electrons orbiting far away. If you stripped out that empty space and packed only the neutrons together, you'd get something like a neutron star, pure nuclear matter, with no gaps, no electrons, no protons. Just compacted neutron. A single teaspoon of this material would weigh as much as 11 times the combined mass of all 8 billion people on Earth. A typical neutron star is about 35% more massive than our Sun, but squeezed into a sphere barely the width of Manhattan. Calling it dense doesn't even begin to describe it. For reasons still not fully clear to astrophysicists, this extreme environment gives birth to immensely powerful magnetic fields. And that magnetic intensity plays a crucial role in the pulses we detect from Earth. To understand how these signals are produced, we need to explore one of the most mind-bending processes in astrophysics. An exponentially growing cascade of light and matter that begins with a single electron. Near a neutron star's magnetic poles, an electron can accelerate to near light speeds. As it moves, it emits what's known as a curvature photon, light that shoots tangentially along the magnetic field line. This emission marks the birth of a pulse. The curvature photon continues traveling until the angle between its motion and the magnetic field becomes too steep. Once that critical angle is reached, the photon dissipates, transferring its energy into the surrounding quantum field. At that point, an electron and its antimatter twin, a positron, spring into existence. This new pair of particles has a small sideways momentum relative to the magnetic field lines, which they shed in the form of synchrotron photons. These photons, in turn, can create even more electron-positron pairs. Once they reach their own threshold angle, the process repeats rapidly, forming a self-replicating chain reaction that multiplies photons and particles exponentially, a brilliant, blinding avalanche of radiation known as a pair production cascade. Eventually, when the photons lose enough energy, the cascade ceases. The surviving photons then stream out into space, while the original electron continues to generate new curvature photons as it travels, spawning additional cascades along its path. This explosive chain reaction is the reason pulsar light is so extraordinarily bright that we can detect it from thousands of light-years away. But why do we perceive this light as periodic flashes instead of a constant glow? The answer lies in the geometry of the neutron star itself. The magnetic poles of a neutron star are rarely aligned with its rotational axis, much like how Earth's magnetic north doesn't match its geographic north. As the star spins, the beams of radiation emitted from its poles sweep through space, just like the rotating beam of a lighthouse. When one of those beams crosses Earth's line of sight, our radio telescopes record a pulse. The light we detect is actually radio light, electromagnetic waves with very long wavelengths. These waves oscillate together in harmony and are highly polarized, meaning their electric fields are aligned in a consistent direction. This alignment is a distinctive fingerprint of neutron stars, and exactly what we see in the mysterious 22 minutes. What's more, within each burst, there are brief fluctuations lasting between 0.2 and 4 seconds, during which the polarization flips by 90 degrees before snapping back. This sudden shift is yet another signature of those powerful cascades happening near the magnetic poles. With so many indicators pointing toward a pulsar, one might assume the case is closed. But there's one stubborn anomaly: the source's extraordinarily slow rotation rate and its exceptional stability. Here's the issue: as pulsars radiate energy outward, they inevitably lose momentum. Conservation of energy demands that they slow down over time. Eventually, they decelerate so much that they can no longer sustain the pair production cascades. Their beams fade, and the pulsar dies. Astronomers call this region of inactivity the death valley. In a graph where the x-axis represents a neutron star's rotation period, and the y-axis represents how fast that period is changing, the death valley appears as a gray band across the middle. Any pulsar whose parameters fall below this threshold should be silent, its light extinguished. But GPMJ 13910 doesn't fit the pattern. Its data point sits below even the lowest line marking the death valley. In theory, it shouldn't be shining at all. And yet, here we are, still detecting it, bright and defiant among the countless silent stars nearby. Typical pulsars rotate astonishingly fast. Most of them spin anywhere from 10 times per second to roughly once every second. By contrast, this mysterious source, GPMJ 13910, turns only once every 1,318 seconds. That's a rotation rate more than 1,000 times slower than the norm. If it were decelerating rapidly, that would at least make sense. Its energy loss could feed the pair production cascades that generate its light. On a graph, that scenario would shift the data point upward, above the so-called death valley. But the problem is, this object isn't slowing down at all. It's unbelievably steady. So stable that it defies the logic of known neutron star physics. Perplexed, astronomers explored other explanations. Perhaps they thought it might not be a typical pulsar, but something even more exotic. A magnetar. Magnetars are neutron stars, with magnetic fields tens of thousands of times stronger than even the weakest ordinary neutron stars. These magnetic monsters are known for their violent starquakes, sudden, catastrophic ruptures that occur when immense magnetic stress causes the crust of the star to snap. These stresses arise from two factors: the magnetic field itself and the gradual slowing of the magnetar's spin. When a magnetar rotates rapidly, centrifugal forces make it bulge slightly at the equator. As its rotation slows, that bulge must settle, forcing the star's crust to realign to a new equilibrium shape. When the crust shifts, it can cause magnetic field lines to twist and reconfigure, unleashing bursts of energy that we can detect as bright flashes of radiation. One such event, from the magnetar SGR 1806-20 in 2004, released an almost unimaginable amount of energy, so much that if it had occurred just 10 light-years away, the resulting radiation could have caused a mass extinction on Earth. If anything could revive the light of a dead pulsar, an event like that would certainly qualify. So could GPMJ 11839-110 be a magnetar that recently experienced one of these colossal starquakes? Could that explain the 22-minute pulses? Unfortunately, the evidence doesn't fit. Starquakes also produce intense bursts of X-rays, yet none have been detected from this source's location, roughly 118,000 light-years from Earth. Even more problematic, magnetar outbursts are short-lived. Their energy fades within a few months or, at most, a few years. It's inconceivable that such a phenomenon could continue shining steadily for more than 3 decades. This rules out even the magnetar theory. Whatever is generating this signal, it isn't behaving like any known type of neutron star, not even a supermagnetic one, undergoing a rare event like a quake. So what else could be responsible for these strange, persistent 22-minute pulses? Astronomers proposed a few alternate ideas. One candidate is a highly magnetic white dwarf, the dense leftover core of a medium-sized star that didn't have enough mass to collapse into a neutron star. White dwarfs can also emit radio waves if their magnetic fields are strong enough. Unlike neutron stars, they rotate far more slowly, which could explain the measured spin rate and stability of this signal. However, there's a catch. To produce a radio beacon as bright as this, the white dwarf would need a magnetic field stronger than any ever recorded. The only confirmed white dwarf that acts as a radio pulsar, known as AR-SCO, emits radio waves about 1,000 times weaker than those from GPMJ 18. That massive brightness gap makes the white dwarf explanation unlikely. Astronomers also considered other possible sources of low-frequency radio emissions, such as interactions between a star and one of its orbiting exoplanets, or between two brown dwarfs locked in a tight binary orbit. But these types of emissions are drastically weaker, roughly 100 million times dimmer than what's being detected from the 22-minute signal. In the end, none of these theories fit perfectly. Every explanation fails in one way or another. The 22-minute pulses of GPMJ 11839 remain a cosmic enigma. But far from being discouraging, that mystery is precisely what excites astrophysicists. When a discovery defies everything we think we know, it forces science forward. This signal challenges our already fragile understanding of neutron stars and stellar remnants. And given how easily astronomers found this one, they believe there are likely many more such sources hidden across the galactic plane, waiting to be uncovered. Perhaps they're already buried in decades of archived data, overlooked because they don't fit expected patterns. Finding more of these unusual signals could revolutionize our understanding of how energy is emitted beyond the so-called neutron star death valley. Whatever process drives these pulses might reveal an entirely new class of celestial phenomenon, something humanity has never observed before. And isn't that what makes this field so thrilling? Every time we stumble upon something inexplicable, the universe opens another door. So what do you think could be behind this mysterious 22-minute signal? Share your thoughts in the comments below. Now, everything we've discussed so far builds on ideas we've explored in previous videos, but the cosmos never stops surprising us. In recent years, new space missions and observatories have uncovered mind-bending discoveries almost every week, from stunning new images of distant galaxies to breakthroughs reshaping our understanding of physics, space research is evolving faster than ever. To keep up, we've launched a free weekly astronomy newsletter that highlights the most fascinating discoveries, even the ones that don't make the mainstream headlines. You can sign up using the link below. A new edition lands every Thursday, bringing the universe right to your inbox. But before you go, here's a mind-stretching question. What would actually happen if you stood on a neutron star? Neutron stars contain the densest known matter in the universe, excluding black holes, which are so extreme they defy our physical laws altogether, a topic for another day. These stars are the remnants of once massive suns that exploded in spectacular supernovas, leaving behind ultra-dense cores. A single neutron star can pack up to 3 times the mass of our sun into a sphere only about 12 to 30 kilometers. The material inside is called neutron degenerate matter, matter composed purely of neutrons squeezed so tightly together that there's no empty space left. To put that density in perspective, a matchbox filled with this material would weigh about 3 billion tons on Earth. Now let's think about weight. When we say we weigh something, what we're really describing is how gravity pulls on its mass. If you say you weigh 70 kilograms, that number actually represents your mass. Your weight changes depending on the strength of gravity. On Mars, for example, you'd still have a mass of 70 kilograms, but you'd weigh less because gravity there is weaker. On a neutron star, things are very different. Because so much mass is concentrated in such a small volume, its surface gravity is roughly 200 billion times stronger than Earth's. That's 2 times 10 times our planet's gravitational pull. If you were to fall just 1 meter on the surface of a neutron star, you'd hit the ground at an almost unimaginable speed, about 1,500 kilometers per second. The gravity would be so intense that even light itself could curve around the star, meaning you could theoretically see the entire neutron star's surface from a single point. So even though it's purely hypothetical, if I somehow stood on the surface of a neutron star, my weight would skyrocket to 200 billion times what it is on Earth. Just imagine the crushing force I'd be exerting on that ultra-dense surface. Not that the star would even notice. Its matter is so densely packed that my body would instantly flatten at the atomic level, likely transforming into neutron degenerate matter as my atoms are squeezed out of existence. This overwhelming gravity also makes neutron stars some of the most perfectly shaped objects in the known universe. Near flawless spheres, smoother than anything else we've ever observed. Roughly 800 light-years away, there's one such neutron star quietly doing something extraordinary. It's called Geminga, and it's been bombarding our planet with antimatter, specifically a stream of high-energy positrons. These tiny particles of antimatter zip across the cosmos before colliding with Earth. For most of history, we had no clue this invisible source existed. The positrons were slipping by undetected, absorbed by our planet's atmosphere. That changed in 2011 when NASA activated the Alpha Magnetic Spectrometer, a cutting-edge particle detector mounted 200 miles above Earth on the International Space Station. And what did it find? You guessed it, positrons. At first, their detection wasn't surprising, but the sheer number of them was. The AMS was recording far more positrons than could be explained by typical sources, like cosmic rays or natural radioactive decay. The data simply didn't add up, so the question became, where was all this antimatter coming from? Only recently have scientists managed to trace the culprit behind this cosmic downpour of antimatter. The trail leads to another high-energy mystery, a peculiar gamma-ray haze known as Geminga, first detected in the night. But what exactly is this strange source of gamma radiation, and how is it connected to the massive surplus of positrons striking our planet? I'm Alex McCone, and you're watching Astro. Today, we're tuning into the mysterious frequency of Geminga, the enigmatic object whose gamma glow has fascinated astrophysicists for decades. Up in the night sky, tucked within the Gemini constellation in the northern celestial hemisphere, lies something truly extraordinary. In 1972, NASA's Small Astronomy Satellite 2, or SAS-ES2, detected an unidentified burst of gamma radiation. With the limited technology of that era, scientists could only narrow it down to a wide region of the Milky Way. The precise source, however, remained lost among the stars. Still, it needed a name. In 1976, Italian physicist Giovanni Bignami coined Geminga, a clever fusion of Gemini, its celestial neighborhood, and gamma, the radiation it emitted. Coincidentally, in Bignami's native Milanese dialect, Geminga also means, "it's not there," a fitting title for an invisible haze, with no clear source. Bignami dedicated much of his career to solving the Geminga mystery. His persistence paid off in 1983, when his team detected a faint X-ray signal from the same region, using the Einstein X-ray observer. This breakthrough allowed them to narrow the search, but the real identity of Geminga remained elusive. Then, in 1991, came the true turning point. Two separate missions picked up radiation from Geminga, and this time, it wasn't steady, it was pulsing. The first clues came from ROSAT, short for Röntgensatellite, meaning X-ray satellite in German, which spotted X-ray pulses. Soon after, NASA's EDRIT, Energetic Gamma Ray Experiment Telescope, aboard the Compton Gamma Ray Observatory, confirmed similar pulsations in gamma ray. For the first time, astronomers realized these signals were linked. Both the X-rays and gamma rays were coming from the same source. Even more astonishingly, the pulses repeated every 0.237 seconds, about 4 times per second. That was the key. Geminga was behaving exactly like a pulsar. A pulsar is a special kind of neutron star that spins rapidly, beaming radiation into space like a rotating cosmic lighthouse. To distant observers, these beams appear as rhythmic flashes, pulses, across the electromagnetic spectrum, from radio waves to X-rays and gamma ray. But back in the early 1990s, pulsars emitting at such high energies were extremely rare. Before Geminga, only 2 others were known, the Crab pulsar and Vela pulsar, and Geminga differed from both in crucial way. For one, Crab and Vela also emitted radio waves, making them detectable with radio telescopes. Geminga, on the other hand, appeared to be radio silent, visible only in X-rays and gamma rays. That made it the first pulsar of its kind ever discovered. Secondly, both Crab and Vela were surrounded by bright nebulae, glowing remnants of the supernova explosions that birthed them. Geminga had none, its surroundings were eerily empty. So what made Geminga's behavior so unique? Why did it seem invisible to radio telescopes? And where was its missing nebula? Part of the answer lies in how we'd been searching. Radio telescopes in the 20th century were limited in sensitivity and range. They typically scanned between 430 MHz and 1600 MHz, missing much of the lower frequency spectrum. But radio pulsars don't emit evenly across all frequencies. Their brightest emissions often peak between 100 and 200 MHz, much lower than what our telescopes were tuned to detect. To make matters worse, these low frequencies weaken as they travel through space, scattered and absorbed by the interstellar medium and the ionosphere. By the time they reached Earth, the signals were so faint they went unnoticed. It wasn't until 1997 that scientists finally realized the truth. Using a highly sensitive transit antenna at the Pushchino Radio Astronomy Observatory, 3 independent research teams detected extremely faint radio pulses from Geminga right around 100 MHz. Geminga hadn't been truly silent, we'd just been listening on the wrong frequency. That same year, astronomer Janis Gill and his team proposed another explanation for Geminga's long-standing radio mystery, its magnetic field. A model later revealed that Geminga's puzzling silence in most radio frequencies could be explained by how its own magnetosphere interacts with radio waves. Within that intensely magnetized region, radio emissions are likely absorbed or refracted, allowing only the faintest frequencies, around 100 MHz, to escape and be detected. This means Geminga would appear completely quiet in the higher frequency bands that most telescopes had traditionally been scanning. Confirming that Geminga was indeed a pulsar, and more specifically a gamma-ray pulsar, was a major milestone in astrophysics. Roughly 99% of its total energy output lies within the gamma-ray range, making it one of the brightest known gamma-ray sources in our galaxy. What we're seeing today is essentially all that remains of a once massive star, several times the size of our Sun, that exploded in a supernova about 350,000 years ago. But Geminga's weak radio signal and lack of a visible nebula weren't the only oddities setting it apart from typical pulsars. Italian astrophysicists, including Giovanni Bignami, the very scientist who named Geminga, made another remarkable discovery while comparing observations from the European Southern Observatory's 3.6-meter telescope and the New Technology Telescope with data from the Canada-France-Hawaii telescope. They found that Geminga was moving, and not just a little. It was zipping through space at a surprisingly high speed of about 0.2 arcseconds per year. To put that in perspective, an arcsecond is an incredibly fine unit of angular measurement, far smaller than a degree. There are 60 arc minutes in a degree, and each arc minute is further divided into 60 arcseconds. Astronomers rely on these tiny measurements to track how objects slowly drift across the night sky from Earth's point of view. Think of it this way. If you traced the moon's orbit around Earth as a full circle, that path would be 360 degrees. At any moment, assuming a clear horizon, you can see about 180 degrees of that sky, half the celestial dome. From the horizon to the zenith, directly above your head, spans 90 degrees. Now hold out your pinky finger, at arm's length, and close one eye. The tip of your finger roughly covers 1 degree of the sky. Try this next time you're stargazing. Your fingertip should just about cover the moon, which only spans about half a degree, or roughly 31 arc minutes across. So when we say Geminga is traveling 0.2 arcseconds per year, it may sound minuscule, but in cosmic terms that's incredibly fast. Most stars appear to move only a few thousandths of an arcsecond each year, from our vantage point. Yet, despite being roughly 800 light-years away, Geminga will drift an apparent 30 arc minutes, the same width as the moon, across the sky in just over 10,000. That translates to a real velocity of nearly 210 kilometers per second, a stellar corpse racing across the galaxy, toward the border between the constellations Gemini and Leo. At its current pace, Geminga will remain within Gemini for another 500,000 years, though it may need a new name after that. But Geminga's story doesn't stop there. It gets even stranger. Its incredible speed led to the discovery of yet another remarkable feature. As it hurtles through the interstellar medium, Geminga trails behind 2 ghostly X-ray tails, stretching an astonishing 3 trillion kilometers across space. Though Geminga is nearly silent in radio frequencies, it roars in gamma rays and X. In 1999, the European Space Agency's X-ray multi-mirror mission, XMM Neutron, was launched to study the X-ray universe in greater detail. 4 years later, in 2003, a team led by Patricia Caraveo discovered these comet-like X-ray trails, emanating from Geminga. Their shape and glow were partly explained by the shock wave generated as Geminga plows through space, coupled with its rapid pulsar rotation. But they also revealed something deeper: the star's enormous mass. Despite measuring only 20 to 30 kilometers across, Geminga is unbelievably dense, packing in about 1.5 times the mass of the Sun. To visualize that, if you scooped up just 1 teaspoon of neutron star matter, it would weigh roughly 4 billion tons, equivalent to 10,000 Empire State Buildings. As this super-dense object speeds through a region of space, containing only 0.06 to 0.15 atoms per cubic centimeter, it compresses both the surrounding interstellar medium and its own embedded magnetic field by a factor of. Meanwhile, Geminga's relentless spinning accelerates electrons and positrons, their antimatter counterparts, to extreme energies, powerful enough to emit bursts of high-energy gamma radiation. While most of these particles escape as gamma rays, others become trapped within the star's magnetic field, spiraling around it. Computer simulations show the twin X-ray tails, trailing along the edges of Geminga's 3-dimensional shockwave, like the turbulent wake left by a ship plowing through water. But in this case, the ship has more mass than our Sun, and its wake glows in blinding X-ray light. Yet, one final piece of the Geminga puzzle remained missing, until that's when astronomers finally detected its nebula, taking the form of a shell of neutral hydrogen gas, roughly 0.4 parsecs wide. This structure turned out to be a pulsar wind nebula. Such nebulae are created by streams of plasma, charged particles blasted out from a pulsar's magnetic poles, and accelerated to nearly the speed of light. These high-energy particles swirl around the pulsar, producing intense X-ray emission. With the discovery of this nebula, Geminga's identity as a true pulsar was definitively confirmed, but the story didn't end there. NASA's Chandra X-ray Observatory took things a step further by not only imaging Geminga, but also comparing it to another pulsar, known as BIT. Both objects were about 500,000 years old, and spun at roughly 4 to 5 rotations per second, yet they appeared strikingly different. Geminga shone brightly in gamma rays, but showed no strong radio emissions, while pulsar B was exactly the opposite, a radio powerhouse but invisible in gamma rays. How could two such similar pulsars behave so differently? Astronomers discovered that the answer likely lies in orientation, the angle at which each pulsar's beams are pointed relative to Earth. Just like Earth, pulsars have magnetic poles near their spin axes, and their radio beams originate from these magnetic poles. To visualize this, imagine a foam ball pierced straight through its center with a wooden skewer. The skewer represents the pulsar's spin axis. As you rotate the ball, an equatorial band forms around its middle. That's where the gamma-ray emission zone, called the torus, exists. Now cut a hole in a paper plate and slide it over the foam ball. That plate represents the gamma-ray disk, radiating outward from the equator in all directions. In Geminga's case, the edge of the plate, the gamma-ray disk, happens to be pointed directly toward us, so Earth lies within its beam path. But for pulsar B, we're looking at the plate face on. Its gamma rays travel sideways, missing Earth entirely. Instead, we see its radio beams, which are angled more toward our line of sight. This simple geometric difference, the orientation of the pulsar's beams relative to us, might explain why Geminga dazzles in gamma rays, while its sibling shines in radio waves. Let's take another look at the two Chandra X-ray images, Geminga on the left and pulsar B on the right, alongside artist interpretations of how astronomers believe their pulsar-winged nebulas might appear. In the visualization of pulsar B, you can see those long, vivid blue tails stretching outward. These represent the radio jets streaming from the pulsar's magnetic poles, shown by the skewers extending from both ends. But unlike a rigid wooden skewer, these jets don't stay straight. Pulsar B is hurtling through space at such a tremendous speed that its once straight jets appear bent backward, trailing like windswept banners behind a racing ship as it moves through the cosmic medium. Now focus on the Geminga image. You'll notice twin elongated tails extending out on either side. Those too are its radio jets. But in this case, they don't aim toward or away from Earth. Instead, they flare outward sideways, suggesting that Geminga's orientation sends its radio emissions in directions that miss our line of sight. So here's the key distinction. When astronomers observe Geminga, they detect intense gamma-ray radiation coming from its equatorial region. Yet the radio jets, directed to the sides, remain invisible from our vantage point. With pulsar B, it's the opposite. Its radio beams are nearly aligned with Earth, making them brilliantly visible, while its gamma-ray zone misses us entirely. Sometimes the simplest explanation turns out to be the right one. And that brings us back to one of the most enduring cosmic mysteries, the strange surplus of antimatter bombarding our planet. For over a decade, a powerful particle detector, known as the Alpha Magnetic Spectrometer, AMS-02, has been mounted on the International Space Station, quietly collecting invaluable data about antimatter, dark matter, and cosmic rays. To recap, cosmic rays are energetic, high-speed fragments of atoms, protons, electrons, and heavier nuclei, racing through space at nearly light speed. They can be produced by supernova explosions, the sun, and various other extreme astrophysical phenomena. In 2013, the MS-02 team announced its first major results. The instrument had detected more than 400,000 positrons, the antimatter counterparts of electrons, marking the largest cosmic ray positron sample ever recorded, increasing the world's dataset by nearly 100-fold. For years, many scientists hoped this excess of positrons could be the long-sought clue to dark matter, possibly created by dark matter particles annihilating each other. Such a discovery could have revealed unprecedented insights into the mysterious material that makes up roughly 27% of the universe. Dark matter, like ordinary matter, possesses mass and gravitational influence, yet it neither absorbs, emits, nor reflects light in any way we can directly observe. Some theories suggest it could consist of entirely new, undiscovered types of particles. So when the AMS-02 detected that strange antimatter abundance, many physicists believed they might finally be glimpsing the footprints of dark matter. But as time went on and data grew, the excitement faded. Deeper analyses revealed that the positrons detected near Earth didn't behave as dark matter byproducts should. Instead, all evidence began to point elsewhere, toward pulsars. For years, astrophysicists had quietly suspected pulsars might be responsible for generating positrons. But solid proof was missing, until that's when the High-Altitude Water Cherenkov Gamma Ray Observatory, HHH, astronomers discovered a faint halo of gamma radiation surrounding Jaminga, with energies reaching between 5 and 40 trillion electron volts, the exact kind of radiation produced by positron interaction. This marked the first concrete observational evidence implicating a pulsar as a possible source of the antimatter excess. Here's how it works. Pulsars naturally generate a haze of electrons and positrons in the space around them. Their immense magnetic fields pull charged particles from the star's surface and accelerate them to nearly light speed. These hypercharged particles then collide with ambient starlight, boosting those photons to far higher energies, creating the gamma-ray halos astronomers detect. However, based on the size of the halo seen by HHH, that assumption held until a few years later, when astrophysicist Matteo Di Mauro and his team analyzed a decade's worth of gamma-ray data collected by NASA's Fermi Large Area Telescope, a device capable of observing lower energy gamma radiation than by carefully filtering out background emissions from other celestial sources. Di Mauro's team uncovered a stunning discovery: a massive glowing gamma-ray halo surrounding Jaminga, far larger and brighter than anyone had ever recorded. This oblong halo, radiating at around 10 billion electron volts, spanned an incredible 20 degrees of the sky, roughly the same area as the Big Dipper constellation, and it didn't stop there. At even lower energies, the halo appeared even larger. If our eyes could see gamma rays, Jaminga's enormous glow would dominate the night sky, stretching across an area 40 times the apparent size of the full moon. This revelation reshaped everything. Based on the halo's immense scale and intensity, scientists concluded that Jaminga alone could account for up to 20% of the excess positrons detected near Earth. If that's the case, then it's not hard to imagine that other nearby pulsars could explain the remaining 80% of the observed antimatter. This insight didn't solve the dark matter puzzle, but it did unveil a remarkable new truth. The very pulsars once thought to simply blink silently across the cosmos might be among the most powerful particle accelerators in the galaxy. The discovery also ties back beautifully to where this story began. In 1967, astronomer Jocelyn Bell discovered the first pulsar, when those rhythmic radio pulses were so mysterious that some even speculated they might be signals from extraterrestrial civilization. In the nearly 6 decades since then, astronomers have identified thousands of pulsars, each discovery sharpening our understanding of neutron stars, the dense remnants of once massive suns. When Jaminga was first recognized as only the third known gamma-ray pulsar, back in 1991, the field was still in its infancy. Today, thanks to NASA's Fermi mission, that number has exploded. Astronomers have now cataloged over 300 gamma-ray pulsars. And yet, given Jaminga's history of defying expectations and pushing astrophysics forward, it's hard not to believe this enigmatic object still has more secrets waiting to be uncovered. It's much more plausible that the strange fluctuations we've observed share a single origin, namely, that the photons emitted from both pulsars are being subtly distorted as they ride the same gravitational waves passing through them. By studying how these pulsar pairs correlate based on their angular distance across the sky, scientists can test this idea. If no gravitational wave background existed, we'd expect zero correlation, a clean, flat line on the graph. But if the data forms a very particular curve, known as the Hellings and Downs curve, that would be the smoking gun, clear evidence of a gravitational wave background shaping those tiny timing variations. And that's exactly what the NanoGrav collaboration managed to achieve. On June 28, 2023, After more than 15 years of precise, uninterrupted monitoring of 68 pulsars, the team announced something monumental: strong evidence for the presence of a gravitational wave background. This right here is the graph astrophysicists have been chasing for decades. It's the unmistakable signature of gravitational waves, waves that literally stretch space in one direction while compressing it in another. The nanograv data displays this distortion pattern beautifully. When two pulsars lie at right angles from each other in the sky, their photons are tugged in opposite ways as they journey to Earth, perfectly matching theoretical predictions. Now, the error bars in the measurements might look pretty large, but don't be fooled. The team's analysis shows that their findings reach a 3 sigma confidence level, meaning there's only a 1 in 1,000 chance that the signal is a coincidence or random noise. In physics, the gold standard for a confirmed discovery is 5 sigma, but 3 sigma is still a solid indicator that we're on the right track. As Nanograv continues gathering data and refining their models, those uncertainties will shrink, and eventually, we could see an official confirmation of a cosmic gravitational wave background. So, what secrets might this background hold? While we can't yet separate its individual sources, scientists believe these subtle ripples could help us listen to the deep cosmic symphony of merging supermassive black holes, and perhaps even unlock clues about the formation of the early universe itself. Until that day, astronomers will keep using this galaxy-sized detector, patiently measuring how our solar system bobs and drifts through the invisible, undulating ocean of space-time. Have you ever heard of nanograv before? What do you think these gravitational waves could ultimately reveal? Drop your thoughts in the comments, I'd love to hear them. Every year since 2018, astronomers have spotted something equally mysterious: a brilliant blue flash lighting up the cosmos. One of the brightest and most powerful events ever recorded, so luminous that an ordinary supernova would look like a faint spark beside it. Some have erupted relatively nearby, others appeared billions of light-years away. They share similar traits, yet no one truly knows what they are, or what causes them. Through years of data and analysis, scientists began piecing together a tentative explanation, until 2023, when one of these explosions completely shattered expectations. They're called luminous fast blue optical transients, or LFBOTs, and there's truly nothing else like them in the known universe. I'm Alex McCone, and you're watching Astro. Today, we're diving deep into the mystery of space's brightest explosions, exploring how they were discovered, and why they continue to defy even our best scientific models. Because these events are so newly discovered, the amount of data we have on them is still minimal. The first LFBOT was detected only in 2018, and since then, astronomers have observed just a handful more. That makes defining them precisely rather difficult. For now, scientists agree on a few shared characteristics. They emit predominantly blue light, display immense optical brightness, and shine strongly across X-ray, ultraviolet, and radio wavelength. And true to their name, they're fast, cosmic flashes that blaze to peak brightness and fade again in mere hours or days. Supernovae also brighten and fade, but their glow typically lasts weeks or months. That's what makes LFBOTs so elusive. Their short lives make them incredibly hard to catch in action. So how did we manage to spot something so fleeting? The discovery came thanks to NASA's deadliest HKO telescope in Hawaii, part of an early warning system designed to scan the sky multiple times each night for potential asteroid impact. On June 16, 2018, deadliest detected something extraordinary, a flash 100 times brighter than a normal supernova, that faded within just a few days. The race was on. Astronomers across the globe scrambled to analyze the data. They traced the explosion to the Hercules constellation, roughly 180 million light-years away, and officially cataloged it as AT 2018. At first, the event was classified as a Type IB supernova, a typical core collapse explosion that occurs when a massive star's internal pressure fails to support its own weight. But something didn't add up. When researchers examined the cow's light spectrum, they found it was far from ordinary. The spectral lines were unusually broad, and the helium lines were weak. It didn't fit neatly into the known Type IP pattern, It looked more like a type I PPL supernova. Yet, even that reclassification didn't hold up under scrutiny. The deeper scientists dug into the data, the more they realized this explosion was unlike any supernova they'd seen before. For starters, it appeared out of nowhere. Its brightness peaked within days, whereas a normal supernova takes months to ramp up and fade. And it wasn't just fast, it was staggeringly bright, between 10 and 100 times more luminous than the average supernova. Even its shape defied expectations. Supernovae typically explode in a roughly spherical pattern, though strong magnetic fields can distort this symmetry. But the cow's explosion wasn't merely distorted, it was the most asymmetrical blast ever observed. Naturally, alternative explanations started pouring in. Some suggested a black hole tearing apart a passing star. Others proposed it was a supernova that had somehow given birth to a black hole, or neutron star in the process. But with just one example, it was impossible to be sure. As the saying goes, once is an anomaly, twice is a coincidence. 3 times is a pattern. What researchers really needed were more of these events to compare. Luckily, they didn't have to wait long.